Hello everyone. Have you ever noticed how a swing always tries to come back to the middle, even if you push it a little too hard? That's simple harmonic motion in action, and it all boils down to one simple rule about forces. Here's a fun thought. Why did the spring break up with the mass? Because it couldn't handle being stretched too far. Now, simple harmonic motion, or SHM for short, is guided by a special kind of force, a restoring force. What is that? It means the force always tries to pull the object back to its starting point, called the equilibrium. In fact, this restoring force is directly proportional to the displacement, which is how far the object has moved from that equilibrium, but here's the catch: it acts in the opposite direction. We write this as force is proportional to minus x, where x is the displacement. To put it mathematically, the force equals minus k times x. The letter k is called the force constant or spring constant. Think of k as a measure of how stiff or tight the spring or system is. A big K means a stiffer spring. The negative sign means the force always pulls back toward the center, never pushing away. If you imagine a graph with force on the vertical axis and displacement on the horizontal axis, you'll see a straight line passing through the origin sloping downwards, showing this negative relationship. This simple, straight line relationship forms the physical foundation of SHM. You can find it in many systems like springs bouncing or even pendulums swinging gently. So next time you see a guitar string vibrating or a skipping rope swinging, remember, this force law is quietly at work. Ready for a little detective work in physics? Let's connect what we just learned with Newton's famous law. Remember, Newton's second law says that force equals mass times acceleration. That's the letter m for mass multiplied by the acceleration a. For SHM, we already said the force is minus k times x. So if the net force equals both expressions, then m times acceleration equals minus k times displacement. But acceleration isn't just any movement, it's the second derivative of displacement with respect to time. Translating that, we write mass times the second derivative of x with respect to time equals minus k times x. This equation may sound fancy, but it's just saying that the acceleration depends on how far and in what direction an object is from equilibrium. Rearranging, we get a second-order differential equation, the second derivative of x plus k over m times x equals 0. This equation is special because its solutions describe oscillations, the back and forth dance of the object. And here pops up a new symbol, omega squared equals k over m omega. That's the Greek letter. Squared gives us the angular frequency of the oscillation, basically how fast the object swings or vibrates. So Newton's law doesn't just apply to moving cars or thrown balls, it also elegantly explains why a spring oscillates when stretched and released. So what exactly does the solution of our second derivative equation look like? The answer is beautifully simple. It's a combination of sine and cosine waves, the same friends that describe waves on the sea or sound waves. The general expression for displacement as a function of time is x of t equals capital A times cosine of omega times t plus capital B times sine of omega times t, where t is time in seconds. But since cosine and sine are closely related, we can rewrite this neatly as a single sine wave with an added phase. So x of t equals x sub m, that's the maximum displacement or amplitude multiplied by sine of omega times t plus phi, where phi is the phase constant determined by how the oscillation started. Both amplitude and phase shift depend on initial conditions, like where and how fast the object was pushed or pulled initially. This formula is the math behind many real-world oscillators, from a mass attached to a spring bobbing up and down to a gently swinging pendulum. It captures that smooth, periodic motion we see all around us. Here's an interesting twist. acceleration and restoring force are more closely linked than you might think. Since acceleration is the second derivative of displacement, mathematically it's equal to minus omega squared multiplied by x of t. In other words, acceleration is always in the opposite phase of displacement. When displacement is positive, acceleration is negative and vice versa. Written out, acceleration of time t equals minus omega squared times x sub m times sine of omega t plus phi. The maximum acceleration, which happens when the sine term is plus or minus 1, equals omega squared times x sub m. Because forces follow Newton's second law, restoring force as a function of time equals minus k times x of t, which can be rewritten as minus mass times omega squared times x of t. This shows that both acceleration and force always point opposite to the current displacement vector, like the universe's way of saying, hold on, don't go that far. If you imagine a graph over time showing displacement, acceleration, and restoring force as sine curves, acceleration and force appear perfectly in step with each other but exactly out of step with displacement. Peaks of displacement correspond to valleys of acceleration and force. It's a beautiful, synchronized dance. Let's take a moment to look at what all this means physically. The restoring force is what gives the object the kind of acceleration that keeps it moving back and forth around the equilibrium point, similar to how centripetal force keeps a car on a circular track. This force also stores energy as potential energy, expressed as 1/2 k times x squared, that's 1/2 times the spring constant times displacement squared, which is lowest when x is 0, right at equilibrium. The system naturally wants to settle where potential energy is smallest, so the equilibrium point is stable. Remember, this beautiful linear relationship holds under ideal conditions: no friction, no air resistance, no damping. Real-world forces, like large swings or air slowing down the motion, introduce nonlinearities and complications that make the motion less regular. Think of it as the difference between a perfectly tuned guitar string versus one with a loose knot or a sticky joint. The ideal SHM Force Law helps us understand the basics before tackling more complicated behaviors. To wrap it all up, the key force law for simple harmonic motion is force equals minus k times displacement, restating that the restoring force pulls the object back toward equilibrium with strength proportional to how far you move it. The equation of motion combines mass and force constants as mass times second derivative of displacement plus k times displacement equals 0, which encapsulates the oscillation mathematically. The displacement can be described as amplitude times sine of omega t plus a phase constant, where omega equals the square root of k over m. Correspondingly, the force as a function of time equals minus mass times omega squared times displacement, and acceleration exactly matches this form with a negative omega squared factor times displacement. This restoring force acting opposite displacement ensures the motion is a smooth sinusoidal oscillation. These oscillations happen around the stable point because energy constantly swaps between kinetic and potential forms. The differential equation is a hallmark of SHM, guaranteeing constant frequency and amplitude when ideal. This fundamental principle applies widely, from mass spring systems vibrating gently to simple pendulums swinging at small angles, and even to molecular vibrations where atoms jiggle harmonically. So next time you listen to music, watch a playground swing, or even observe molecules under a microscope, remember SHM's restoring force law is quietly orchestrating this elegant physics concert. That's all for today's journey into the force law for simple harmonic motion. Physics gets even more fun when we learn with a smile. See you in the next lesson.